And
Sorry.
now I'm recorded. Shall I?
No, keep going, keep going.
Today is a great pleasure for me to introduce my colleague, my friend, Weiwei Pan. Weiwei is a research associate at ICS. She's working on machine learning research in data science actionable knowledge lab. She's also teaching AM207, a very well-received course by students, and also supervise undergraduates and master's students in research. If you're interested for working with Weiwei, please contact her. Before becoming a research associate, Weiwei was an assistant professor of mathematics at St. Mary's College, then a master's student at ICS, then an instructor at ICS, then a master's student at ICS, then a postdoc at ICS, and now as a research associate. And in precise this order, as I said it. She has been going in various stages in her career. She is interested in building models with guaranteed properties that align with the task-specific desiderata. Her bio says such as interpretability, risk awareness, satisfaction of domain-specific constraints. I make a little modification for her, so she goes placidly amid the noise and the haze and interpreted what model there may be in silence. As far as possible, without surrender, be on good terms with domain-specific constraints. Okay, let's welcome Weiwei.
Thanks, everyone. Pavlos is clearly working on poetry nowadays. You know, that's his COVID activity. So anyways, yeah, so a pleasure to be here. Thanks for having me. And today we're going to be talking about what are some useful uncertainties for deep learning and then how exactly we're going to get them, okay? And so as motivation, now we know that predictive models are everywhere, right? So the guys, this is not science fiction. They really are, right? It's not scaring you. It's that, you know, you find these models not everywhere in your smart devices, but also in your social institutions. Okay, so for example, in particular, our lab, DTAC, works with healthcare data, as well as domain experts, as well as criminal justice. So you'll find these predictive models all over in your healthcare making predictions that affect you as a patient in the system. And if you end up ever working in the criminal justice system, you'll also find these predictive models, right? And so the one thing that we want, there are many things you want out of a machine learning model, but the one thing we want in our lab, we often say that reliable measure of a model's sense of predictive uncertainty in these high-risk domains is just as crucial as the correctness of these predictions. Okay, so you're like, why do I care about uncertainty? Why isn't it just good to be right? I mean, what's the problem, right? So here's an example. Let's make this more concrete, right? So this is a funny example, and we see this nowadays in literature a lot, right? So let's say that you train a predictive model that will tell you if something is a dog, bird, or airplane or something, okay? So you train it on CFAR, which is a data set consisting of these types of objects, okay? Right? Then you test it on a data set that has images that has nothing to do with the images you trained your model on, okay? So this set of images contains images of license plates, right? So what's your model gonna do? Well, first let's think about what a human would do, right? You train a human to recognize dogs and cats and airplanes, you show them pictures of license plates, they're gonna be like, I don't know, right? Like if you're a student, you might even get mad, right? Start complaining to your dean, right? This is an unfair test, right? You would do something like this, right? But what is a model going to do? Well, a model is going to say, well, I know a couple of bins, I know dogs, I know birds, and I know airplanes. So if you show me something, it's gotta be one of them, right? So it's gonna see pictures of license plates and it will make a precise decision for you. It's gonna call something a dog, something a bird, something an airplane. And if you check the classification probabilities of these decisions, they're gonna be 100%. Right? Not only are they wrong, they are so certain, right? Not even a single doubt in the world, right? This is what we're talking about. Now, when we're making very risk-sensitive sort of decisions, like whether or not to put someone in jail, or whether or not to give you a huge dosage of a potentially lethal medicine, we might want to know how unsure we are about these predictions, right? Just a thought, okay. So cool, so that's the motivation, right? So now you're convinced that we want predictive uncertainties. The question is, where do we get them from? All right, who's going to give them to us? How do we get them from our models? So we're actually going to use as a template for building models with uncertainty, we're going to start with Bayesian polynomial regression, right? So at this point, you might be deeply disappointed because maybe you came here for the deep part of the deep learning, right? We'll eventually get there, but the point of starting with Bayesian polynomial regression, something very unsexy, right, very basic, is that all of the problems that we don't like about deep learning already manifest in this class of very simple models. So the point here is not that the deep part of your deep learning model has gone wrong, okay? It's a simple matter of our metrics, the way that we evaluate our models simply don't line up with our goals of what we want our models to do. Okay, and that can already be seen by using Bayesian polynomial regression models. Okay, then later on, I'm going to really try to convince you why you want to fancy it up. Why isn't polynomial regression just good enough? They're simple, I understand them. Why even do I need a neural network, right? So once that you're convinced that you need these fancy objects called neural networks, then we'll talk about finally, right, our contribution with collaborators, which is scalable Bayesian deep models, and you'll see why the scalable is desirable, or why that you don't get it for free, okay? So that's the plan for today. But first, let's think about some models that we know, that we love, that already give us predictive uncertainties, okay? But before we talk about these models and the predictive uncertainties, let's have a contract between us, you and I, right? Like, what are we talking about when we're talking about uncertainty? How do I know good uncertainty like when I see it? You know what I mean? Okay, so let's get down to that fact first. So first of all, there's two kinds of uncertainty. Maybe you haven't thought about this before, even if you thought about uncertainty, but it turns out if you thought about it, it's not so unusual. Meaning uncertainty usually comes in two flavors because your uncertainty arises from two sources of lack of knowledge, okay? The first source is actually called epistemic uncertainty. And this is the kind of uncertainty due to the fact that you can't be sure how the model ought to behave in a region where you have very small numbers of training data. Like if you've never seen an exam problem type before on an exam, you would have very high uncertainty about how to answer this problem, right? But guess what? The key thing about this kind of uncertainty is that it can be reduced, right? You don't know how to do this type of integral. Well, once you've done it enough times, you're going to have very little uncertainty. You're gonna know how to do it, right? So epistemic uncertainty, the kind of uncertainty that arises from the model being trained not a whole lot on this type of data, can be reduced if we simply show it more instances of the data, right? The other kind of uncertainty, on the other hand, is called aleatoric uncertainty. And this is due to the uncertainty that cannot be reduced, irreducible. It's a fundamental fact of life, which is even if I know the ground truth model that's generating the data, that's capturing the ground truth trend, I can never be 100% sure of my prediction of what Y should be. And why? That's because of the inherent observation noise that's contained in Y, right? Like your predictions are never going to align with real life because there's just too many factors of randomness that you inherently cannot control for, right? So that type of uncertainty is very important that we distinguish aleatoric from epistemic, because epistemic, remember, we can do something about. If you don't like that you have uncertainty, go collect more data, okay? If you have high aleatoric uncertainty, there's nothing you could do. Now you need to manage the inherent risk, right? Okay, so now that we know there's two types of uncertainty, let's look at the simple picture over here and see, like just as humans, one human being to another, figure out what it is that we want out of our predictive uncertainties for models, right? Okay, so here's the training data. They're plotted in the black dots, right? Okay, and then the shaded blue area, that's my predictive uncertainty. So like the larger, right, the width of the shading, it means the more uncertainty I have, okay? So does this sort of uncertainty, given the data, does it look good to you, right? Before we get into metrics and models, just let's first have a goal. What do you guys think? Feel free to unmute yourself and just interrupt anytime. So what do you think about this? Does it look reasonable, my uncertainty? Or is there something you don't like, or is this good? What do you think? Looks reasonable to you. Okay, somebody is like, looks reasonable. Okay, fantastic. Why does it look reasonable? Remember, there are two sources, right? So let's check both. Aleatoric uncertainty. So aleatoric uncertainty is about uncertainty that I have due to the inherent noise in the data, right? So if I have more noise, I should be more uncertain. Okay, let's check that. Well, here I have a lot of data. You see that the data is kind of noisy, right? And you see that my uncertainty, i.e. the shading, kind of just really does encompass that noise, right? So I'm as uncertain as the data is noisy. Check, sounds good to me, all right? So now let's check epistemic uncertainty. Epistemic uncertainty is I'm uncertain, right? Yeah, right, okay, so the epistemic uncertainty is I'm uncertain, right, as I'm observing less data points in that region, okay? So where am I not getting training data? Well, over here, I have no training data. I should be more uncertain, okay? And then over here, I have no training data. Over here, I have no training data. I should be more uncertain there, right? And then do we see higher uncertainty? Yep, we sure do, right? Higher uncertainties in these regions, right? Epistemic uncertainty sounds good. But maybe let me give you one more feature, which is that, look, you know, okay, so technically, like over here, this dot that I'm drawing over here, it's technically OOD, right? Or out of distribution. Like it's technically away from my training data. But don't you agree that it's kind of close, right? I should not have infinite uncertainty here because it looks so awful like my training data in this region, right? So maybe my uncertainty, one more desiderata, is that it should scale as a function of the distance of a new point to the data set, should it not? Right? That seems reasonable, right? Okay, so as in like the more that I'm away from my data points, the more uncertainty I should have. And the closer I am to my data points, the less uncertainty I should have, right? So we want that sort of scaling. Okay, cool. So if you buy that, if you're on board at this point, right, then we at least have a verbal contract of what we want, which is fair, right? If we're going to judge a model for producing this, we should know what we want the model to do. Cool. All right. So what kind of models will give us uncertainty? Well, so how about we think about what kind of models we like in the first place to capture trends in the data, right? Like we said, a model that we know and love is polynomial models. It's literally like just fitting the equation of a polynomial to our data, right? And because we're being probabilistic, we take into account, like we said, right? Like we can never be perfect. We take into account that the actual observed data Y could be different from what we predict using our polynomial model by some random noise amount, right? And we assume a known distribution for this noise, right? This is a common practice in statistical modeling, right? Okay, and the reason I started off with polynomial models is because actually they're just really flexible, right? In some sense, I mean, like, and you'll see in kind of my work, maybe I'm making more of the claim that we should go back to thinking about it more like polynomials rather than neural networks, because what polynomials are is secretly a kernel regression, which is much more flexible, meaning that instead of thinking I'm trying to fit like a 10th degree polynomial to my data, how about you think of it like this, is that actually secretly what you're doing is first you're pre-processing your data. That's what you're doing, okay? What do I mean by pre-processing? You take a look at your data and then you just add more covariates or features into your data. And these features are going just to be the polynomial terms of your data. Like you take an x, so you transform it into x to the 0th power, first power, second power, etc., all the way to the dth power, right? And then after you pre-process your data, all you need to do is fit even a simpler model, a linear model on top of these features that you've just engineered. And now you have a polynomial model, right? Now, if we look at polynomial regression in this way, we are having the flexibility of using any feature map I want. I can transform X as part of my pre-processing process into whatever kind of complicated features I want, right? Then the only model that I really care about, the modeling part, is going to be taken care of by just simply linear regression. This is very flexible, at the same time, really tractable, very simple, right? So this is the point of view that I take when I say a polynomial model. Cool. All right, so how do you fit a polynomial model? Again, stuff just recalling, right? So we want to maximize the likelihood. The idea of modeling noise is that it gives us a distribution of outcomes, right, given our observation and our model parameters, right? So if we have a distribution, if we have a PDF, right, describing the distribution of likely outcomes given my covariate and my model parameters, all of a sudden I have a way to describe the likelihood of my data, right? And so I could seek, right, the best model parameters, the best polynomial coefficients, let's say, right, that maximizes the likelihood of my observed data. And that would be following the maximum likelihood principle if you are into that sort of thing, right? But this is very typical of machine learning. So that's what we're going to do when we say model fitting or finding the best model, okay? So far, nothing controversial, right? But here's the part, right, that's maybe worth thinking about, which is like, great, now you've done the optimization, you found the polynomial coefficients, W1 through WD, right, that maximizes the likelihood of your observed data. Well, you got one answer. Remember, we wanted predictive uncertainties, right? We wanted the y is equal to 5 plus or minus, 0.5. We want the plus and minus part. If you just did maximum likelihood once, you get exactly one answer, right? You get exactly one prediction, which is not what we want. So how is it that you can get predictive uncertainty if you're fitting polynomial models this way? Well, it turns out, right, that there's a very clever way of doing this. You just simply bootstrap, meaning that instead of getting one model by fitting your model once on the data, you slightly change your training data set a little bit, meaning you kind of randomly sample another training data set with replacement from your observed data set, right? So when you randomly sample your data again, you're going to get slight variations. You're not going to get the same point over and over again, right? And so which means that each time you randomly sample your data to create a new training data set, you fit your polynomial model again, you're going to get a different model, right? That's just how it's going to go. So when I do this, instead of getting one model, if I bootstrap, I have the capability of getting, let's say, 100 models. So these are all of degree 10. Okay, so instead of getting one best model that goes through my data, I get 100 plausible models that all kind of go through my data. So what's the advantage of this? Why do I want 100 models? Remember, we're not interested in just predictions. We want uncertainty. Now I can use my 100 models to give me a sense of how much uncertainty I have. And this is how it's going to work, right? I'm going to look at how much my models disagree, right? The variance in the prediction of my models. And when that variance is large, i.e. my models disagree on what the answer should be, my uncertainty will be large, right? And when the variance is small, because most of my models give me the same prediction, then my predictive uncertainty is going to be small, right? Again, not very surprising, right? But this is what we can do. All right, but let me ask you this. So if I do this, if I bootstrap my polynomial model of degree 10 100 times, and this is the kind of uncertainty I get for this toy data set, is that good? I mean, I can do it. I got you the uncertainties. Are these good uncertainties? So remember what we had agreed on, right, before this talk started about what we wanted our uncertainties to look like. What do you guys think? Is this good or not so good? Okay, so somebody is like, this is fantastic. Okay, looking for disagreement. Anybody not like this? People were like, this is great. Anybody not like this?
I mean, it seems expensive to train with big
expensive.
ads.
Right, but you know, like, by the way, Google does this stuff all the time. Like, I saw a paper and I was having this argument, right, with this guy, and he was like, well, you know, I trained 100 models. I did them all in parallel. And I was like, well, if that's what you can do, right, I have no complaints, okay? So that's not exactly my complaint for this. So does anybody not like the shape of my uncertainties here?
So
It seems to be.
Go ahead.
Thank you. So actually, when you are close to the limit, it seems like the uncertainty grows a lot. And you're still close to your data points.
Yeah, there's something real weird. Remember, we said, okay, we want the uncertainty to be higher where there's no data. For sure, this is giving it to us. But remember, we also want to be like reasonable, right? Like, look, if you're this close to the training data, like I'm right here, like 0.1 away. You're telling me your uncertainty is like infinite? That's weird, right? Like, it shouldn't be like that. We want our uncertainties to scale as we move away from the data. Somehow we want it to be the biggest in the middle and maybe smaller, right, towards these ends. And we're not getting that here, okay? Does anyone have a conjecture for what's going wrong? Is it like frequentist statistics going wrong? What's up? So go ahead, yeah.
Aren't you just simply taking every single model that you're producing here equally weighted if you have a distribution?
True.
So
that is the frequentist way, though.
What you've got there seems to be neglect that entirely.
It's true. I definitely am not ever favoring one model versus the other, but that is the frequentist way, right? If we wanted to weigh these models according to some distribution, then we'd be in the Bayesian sort of framework, which will come, right? But maybe one hint is look at how, like, remember again, and this is actually going to be the recurring theme in this talk, which is, where do uncertainties come from? They come from the functions themselves, okay? So if you are like, what's up with my uncertainties? Why is it doing this? Look at what your functions are doing, right? So you got some functions that go all the way like that, and you get some functions that go all the way like this. That's why your uncertainty is cray, okay? Because you've got cray functions, all right? That's what's going on. Okay, so if we don't like those functions, what do we do? Again, common practice, like generally you don't like this sort of functions.
Use simpler ones?
Yeah, you can use simpler ones or you can regularize. So you're thinking that this is an overfitting kind of behavior, right? That's what you're hinting at. That's exactly it, right? So we often go, well, maybe we're just overfitting. The data does not require such complicated function. That's why they're going crazy, okay? All right, well, let's check that out. So first of all, let's think about like regularization, and then we'll think about like simpler functions, right? So oftentimes we don't just go, let's cut back our complexity, right? We go, hey, let's use our crazy function, but let's add some regularization. So let's give it an L2 penalty, okay? So why don't we do that? So that's exactly what I've done. So I've added L2 penalty, and the strength is goes from very small, right, to very large, okay? So very heavily penalized versus very weakly penalized, okay? And this is the kind of uncertainties, the predictive uncertainties I get when I bootstrap. Do any of these look good to you? Some of them. Okay, somebody is nodding their head. Does this one look good? Okay, in the sense that people were like, yeah, sure, this part is wider, right, than that part. True. Okay, maybe by a little bit, right? Maybe you can complain that it's not wide enough, but who knows what that means, right? But are you sure though? I mean, does this kind of uncertainty satisfy our desiderata? Remember, we don't just want wider uncertainty in the gap. We want the uncertainties to scale as we move away from the data, right? Meaning that this doesn't quite satisfy, meaning it's equally uncertain far away from the data as it is close to the data. Okay, it's just binary, yes or no. Am I uncertain or am I not uncertain, right? So somehow this still doesn't satisfy our social contract, you know, like the notion of the definition of good that we built up, okay? And should this surprise you? No. Well, actually, if you think about what regularization does, is that even if you add a little bit of L2 penalty, it's going to want the function to be as smooth as possible. It's not going to allow you to do this sort of interpolation because there's no benefit there. There's no data there. So doing these kind of crazy wiggles is not going to get you to fit the data better, right? So therefore, in the areas where you don't have training data, L2 penalization is asking the function to be as smooth as possible, right? And remember, when you don't have crazy functions, you don't have crazy uncertainties, right? These two things are equivalent. Okay, so actually, so this is very interesting, right? If we do what we commonly do, which is use a very, normal kind of L2 regularization on our complicated models, we actually lose the uncertainties that we're looking for, right? And if you really want to heavy up on your L2 regularization, like you lose uncertainty period, okay? Counterintuitive, right? So again, you don't need a neural network, it's already happening now. Okay, cool. So what about this other thing where you're like, okay, you know, maybe the problem is you're using a degree 10 polynomial. How about you use a smaller degree and maybe you don't even need to L2 regularize, right? So first of all, there's no such thing. Always do L2 regularization. That's my recommendation. But okay, if you insist, that's what we're going to do. We're going to do polynomial model selection. Okay, and you can use AIC, BIC, whatever information criteria you want, or you can do cross-validation, which is what I've done here. Okay, so again, by our verbal contract, right, we already said that this kind of uncertainty, no good. It was just kind of like binary, like infinite or zero, you know, no good, okay? We also agree that degree 3, this kind of polynomial uncertainty, also no good, because I'm equally uncertain in the middle, where it's farthest away from the data, as I am here, where it's closer, okay? So also no good. This is clearly not even fitting the data, so we don't consider that, right? So the degree that we actually want is degree 5, right? That's the thing that satisfies our definition of good, but do we find it if we cross-validate? Meaning that if we do cross-validation, choosing the degree, looking at the average validation MSE, on a held out validation data set, which one do we pick? Well, it turns out that we picked degree 3. That should not surprise you, right? Because degree 3 satisfies Occam's razor. It fits data the best while being the minimum variance, right? So it generalizes the best, okay, on the data that's sampled from a similar distribution as your training data, okay? So what is the lesson here? It means that all of these best practices, such as using cross-validation and Occam's razor to select your model, such as using, what we did before, regularization, right? These are all standard, great best practices. If you do it, you will often select the model that gives you an unsatisfactory form of uncertainty, right? Which is kind of disturbing to us, right? So none of these practices, they're actually directly in tension with what we want. Okay, cool. So maybe your problem is like, okay, you know, maybe just like the problem is that frequentist, like maybe that's just too hard to regularize. Maybe it's unprincipled. What if I did it a Bayesian way, right? Maybe it'll just come out better. Okay, so let's just try that, right? So in a Bayesian model, in a Bayesian framework, instead of like, you know, bootstrapping a million times to get different plausible fits on your data, you inherently bake that into the model. How? Well, by putting a prior, encoding some beliefs about what your parameters of the model should be. Okay, and this prior not only encodes your beliefs, like I think W should be equal to 1, it also encodes your uncertainty about that belief as a distribution, right? So you're already getting the uncertainty baked into the model at the onset because your prior includes uncertainty since it's a distribution, okay? All right, so then using Bayes' rule, right? So now doing maximum likelihood is not gonna make no sense because you have more than a likelihood. You have the prior, you need to take advantage of it, right? So now we use Bayes' rule to infer this object we call the posterior, which instead of giving us one best answer, it gives us a range of answers. So a distribution over plausible models that can fit your data well. Okay, right? And then you'll see that the posterior, if you recall, is obviously a proportional to the product of the likelihood as well as your prior, right? So it takes into account both the data as well as your prior beliefs, okay? All right, so something like I like to remind you, because this is going to come back again, right, in a meaningful way, is that if I choose the likelihood to be normal, like the noise to be normal, and if I choose a Gaussian prior for all of the weights in my kernel regression or polynomial regression model, then the posterior can be obtained in closed form. It's another normal distribution, okay? So why do I care? I mean, sure, this is like a fact from some class you took a while ago. Who cares? You know what I mean? Like, why do I care? Why is that important? That the posterior is a normal distribution, which is nice, right? Because normal distributions are like easy. So why do I care? Anybody have any guesses?
Is it possible that the optimization statement becomes analytically easier to resolve?
Everybody is like analytically nice, analytically nice. Okay, so not only is it that if we want to compute point estimates from this posterior, is it easy because, well, it's a Gaussian. I know lots of things about Gaussians, okay? Not only that, but also this Gaussian is easy to sample from, okay? And that's just using the key fact that if you want to make any sort of statements or infer anything interesting about a Bayesian model, you have to sample, okay? And so in particular, if we want to get uncertainties, predictive uncertainties, we want to get the samples from the posterior predictive distribution. And how do we do that? We just sample like 100 models. Instead of bootstrapping 100 models, we just sample 100 models from the posterior. And here they are, right? They're looking kind of different, okay? And then for each model, we ask each model to make a prediction, right? With some noise. And that's your posterior predictive. That's it. It's very much similar to Bootstrap, except you don't get Bootstrap models. You get a distribution over models, or you get your 100 models by sampling from the posterior. And it's very important that Bayesian kernel regression has closed form posterior because Gaussians I can sample from. I know how to do that, okay? And later on you'll see that I will very quickly not know how to do that. Okay, so if you look at the posterior predictive now of the Bayesian model with the same degree, right, degree 10, you know what I mean? Okay, so remember that was a degree that we did not like for the Bootstrap model, right? These uncertainties all of a sudden, they look better, right? They don't have this sort of infinite blow up kind of phenomenon in the middle. Right? So then maybe at this point, you might conclude being Bayesian is better, right? There is inherently some regularization magic sauce going on here, and that's why it's just better to be Bayesian, right? And sadly, that is just not the case, okay? Because being Bayesian also means you have to choose other types of model assumptions. And one of the design choices is you have to choose the variance of their prior, right, on the W. So last time, the picture that you liked, that was a variance of 40, okay? And now check out if I choose a variance of 10, what does the posterior predictive uncertainty look like? Oh, the posterior predictive uncertainty look bad, right? It's not the kind of thing that we want. So your choice of variance is going to have a huge impact. So then that sort of begs the question, how do we choose the best prior, right? I mean, what metrics can we use in order to do that? And later on, you'll see that there's no metric. That's in terms of getting the best uncertainty. All of our metrics are going to fail. Right, unfortunately, just like in the frequentist case. Furthermore, let me point out one more problem of design choice is that you could have chose a feature map that is different than the general polynomial feature map, right? The general polynomial feature map says turn that x into x1, x2, x3, right, all the way to x to the d, right? I could have looked at the data and decided that, hey, maybe it looks odd degree, right? Maybe I'll just do odd degree expansions. You know, I'm not going to consider even degree, right? You think that would have no effect on the model, you know? But alas, sadly, it does. Because if I choose the wrong feature map, look at my posterior. I get the same function over and over again as I sample from the posterior. And therefore, since functional diversity is directly related to predictive uncertainty, I get no predictive uncertainty in the areas that I want, right? Or not the kind that I want. Okay. So yeah, being Bayesian didn't help because all of these design choices can lead you to the wrong types of predictive uncertainty. So, but let's conclude, right? Because we did learn something here. What did we learn? What we learned is that if we want these sort of nice, wide predictive uncertainties, we need the functions that we get, no matter through bootstrapping or sampling from the posterior, we need them to have diversity, especially away from the data. So meaning that we want the functions to extrapolate very differently as they go away from the training data. No diversity means no uncertainty, okay? So in a Bayesian framework, where does functional diversity come from? Well, so if you think about it, you will conclude that actually it turns out functional, because like it doesn't come from the likelihood. Likelihood just says makes your function go through the data. That's what the likelihood says, right? The only part that's encoding for diverse functions is the prior, okay? So the prior is the thing that encodes the diversity of the function. So this is me, instead of sampling functions from the posterior, this is me sampling from the prior, the P of W, okay? When I visualize that for you, you see that for variance is equal to 40, I get a whole lot of diversity of functions already in the prior, meaning the prior says you can pick from a different diverse class of functions. And that's why in the posterior, I'm going to get a diverse amount of functions, okay? Whereas on the other hand, if I choose the prior to be 10, so sorry, this is the prior is equal to 10, right? Then I'm going to get very few interesting functions in my prior predictive already. This is before I fitted the data at all. Already the prior is telling me I don't get to use interesting functions. I only get to use boring ones. And therefore, should you be surprised that the posterior, the number of functions or the types of functions encoded in your posterior are also similar and boring, right? Not diverse, okay? So what we've learned is that we have to ensure that our feature map along with our prior P of W has to encode diverse functions, okay? That's what we learned. All right, so then the question is, well, how do we do that? Is there a model selection trick that I can do that's going to give me really great uncertainty, epistemic uncertainty? Unfortunately, no, because what is the most common thing that we compute to measure the quality of a Bayesian model? We compute the test log likelihood, right? You know, of new data under a model. And where's the test data coming from? Well, the test data is usually a permutation of your training data, meaning that you're going to sample them from the same places that you took training data from in the first place. And guess what the test log likelihood is going to measure for you? It's going to be like, does your model capture the data very well? Okay, and so you have two models over here, both capture the data very well. So they're going to have about equal test log likelihood, right? So under the test log likelihood, these are equivalent models. But under our new notion of what is good epistemic uncertainty, they are not, because the gray model clearly has the kind of uncertainty we want, right? Whereas the blue one doesn't. Cool. So basically this is saying, I don't care if you're being frequentist, I don't care if you're being Bayesian, most of the tools you use, if not are directly against what you're trying to accomplish, they certainly don't help you find what you want in terms of uncertainty, right? Scary, scary news. Okay, so how do we bring the deep learning part into this talk? Well, so first I have to convince you that you need a deep model, right? So why on earth would you need a deep model? Is polynomials seem great, kernel, regression seems great. Well, it's a feature choice part, right? Is why we need a deep model. Meaning, remember, if you're doing polynomial kernel regression, you have to choose how to transform your x's into features, right? Do you add polynomial, odd degree, even degree? Do you add cosine, sine? What do you do? Right? So it turns out that instead of you deciding what you should do, you should probably pick the features, the ways to transform the data that suits the task the best, right? Like if you're trying to classify whether or not these human faces are male or female or person A or person B, why don't you choose the features, right, from your data that helps you do this classification? Right? And that is exactly what a neural network does for you. It learns a feature map phi that is best for the task that you're trying to solve, right? So again, this is just a quick reminder of what a neural network is that it's a complicated function that we are thinking of as a feature map, right? That's made up by composing very simple functions, right? And each simple function can be represented graphically, right? Which means that when you look at a very complicated graph like this, you're like, oh, I see. This is encoding algebraically a very complicated function, right? Because each one you can recognize as a simple function. And graphically, this is telling you that you're adding a bunch of simple functions together and that you're composing them because you're feeding them into more simple functions. And through this composition, you get algebraic complexity, okay? So a neural network is just a quick syntactic sugar way of building up a very complicated feature map, right? That's what it is. Cool. All right, so again, remind ourselves why we need a feature map. So what part of a neural network represents a feature map? So a neural network, at the end, at the output node, right, we're always going to pretend that from the last layer to the output, this is just simply a linear model, right? Because this is just a bunch of inputs going into a single output and you're just transforming it once. So this is just a linear model. So it's either linear regression or linear classification. All the previous parts of the neural network, right, up to the final layer, up to the semi-final layer, right, that part is what we interpret as the feature map extraction. So that's going to perform some sort of useful transformation of your data into features so that the task that you're trying to solve with this linear model can be accomplished as best as possible. So for example, if you're doing linear classification, meaning classification with a linear boundary, it's going to look at this data and it's going to be like, hey, how do I transform this data set into a data set where we can classify perfectly using a line, right? And you see that this is the feature that we learn, okay? So a neural network automatically learns the feature map phi for you that we needed for kernel regression, okay? Cool. All right, so now that we have fancier models, the question is still the same. What do we want? We want good predictive uncertainties, right? And this is just to remind you that good uncertainty, especially in data poor regions away from the training data, they only come if you have diverse models, if you have models that extrapolate very differently in these regions, right? So how do you make sure that your neural network or indeed polynomial models extrapolate in a diverse sort of way away from your data? Do you get that for free? The answer is no, right? And so this is joint work with some folks in my lab whom I like very much. They're fantastic, but it takes too long to read everyone's names. But you can read these papers online if you want. So I've included the links there. right? So this is a work that says, no, you cannot hope for functional diversity by just doing random restarts and just crossing your fingers and praying, okay? You have to, if you want diversity, you have to actively encourage for it, meaning that if you're gonna train 10 models, not only do you need to have a penalty term in your loss function that says, my 10 models each have to be really good for the data, you need to have a loss function term in there that says, they're also very diverse. And the way that we encode diversity is just by maximizing the cosine angle between the gradients of these functions, right? Which means that the functions are gonna steer away from each other to maximize that cosine angle. Very intuitive, right? See, I'm seeing people nodding, so it's good. Very intuitive, cool. All right, so, and when you do this, what do we learn? Well, we learned that if you do this, this sort of training, we call lit training, which means locally independent, so diversity training, you are able to learn functions that interpolate your data just fine, but extrapolate in diverse ways away from your data, which is fantastic, right? And you get to get the same result for classification. So if there's a data set that there's some ambiguity, you can classify it using this boundary, or you can classify it using the other boundary. These boundaries are quite diverse, right? Using any other existing methods, you're not gonna be able to learn these two diverse boundaries, but using our method, you will. You will be able to learn diverse explanations for your data, okay? Which is pretty cool, right? Okay, so now we know how to get these sort of diverse functions if we're using neural networks, diverse ensembles, right? Which means we're gonna get some pretty good predictive uncertainty. But that doesn't really solve any of the problems we had before or your complaints about neural networks, which is like, yeah, then they get overfit, you know, like if you were being frequentist, then you have to bootstrap, it's expensive, blah, 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 right? I mean, the litany complaint still stands, right? Nothing has changed. If anything, things have gotten worse because you have a neural network. So maybe let's consider the Bayesian framework again. Maybe the Bayesian way will be better here, okay? Let's think about that for a second. Well, what does it mean to be Bayesian in the context of your likelihood as a neural network? It's the same thing, is right? So you have essentially just priors over your weights. Now you have a neural network, they have weights, you're gonna put priors over each one of those weights. That's what you're gonna do, okay? And when you do that, what you have is called a Bayesian neural network. And the key thing to notice here is, unlike for Bayesian polynomial regression, you don't have the closed form expression for the posterior. Okay, and if you remember why we cared about it at all, is because in order to go to get those nice predictive uncertainties from the Bayesian model, we need to sample models from the posterior, right? So if I don't even know what the posterior is, I can't call it by its name, there's no way I can numpy.sample anything from it, right? That's just how it's gonna be, okay? All right, so, but before we handle this issue of how do we sample the posterior from Bayesian neural networks, but let's think about, is Bayesian neural networks even capable, right, of capturing the kind of uncertainties we want, right? So this is just helping you to recall that, remember, you get good predictive uncertainties, like wide uncertainties, if, right, your posterior can describe very diverse functions. And where do those diversity comes from in your posterior? They come from your prior. So if your prior already encodes for very diverse functions, you're gonna get those diverse functions in the posterior, right? So this is me sampling from the prior predictive of the Bayesian neural network. Literally just me sampling random weights from my prior and then making predictions to see what they look like. And you'll hopefully agree that these functions look pretty diverse. They look pretty different, right? So there's a real good chance that if we can do this inference correctly, we're gonna get the type of posterior diversity we want, okay? All right, so what does it mean to do this inference correctly? Because I already told you, I can't give it to you in closed form, the posterior, so what are we gonna do? Well, it turns out that there's generally two approaches to work with intractable posteriors, like posteriors that I don't know the closed form for. Either you can sample, i.e. approximate the posterior with a set of samples that you obtain from something like MCMC, never mind if you don't know what that is, or variational inference. What that is you're gonna take an easy distribution like a Gaussian, okay? You know your posterior is not a Gaussian, fine, I don't care, right? But just take a Gaussian because I know how to sample from a Gaussian, right? Then you're going to use this Gaussian to approximate your true posterior, and you're going to do the best you can, right? This is kind of like saying, you know what, I'm never going to get the posterior, but I'm just going to do the best I can with a simple distribution. At least I can sample from the simple distribution, right? And in the future, instead of working with your actual true but intractable posterior, you're going to work with your approximate posterior Q, okay, which is the Gaussian, right? Okay, cool. Right, so then you're like, wait, how is this valid? How can you just take a complicated thing, approximate it with a really simple thing and get any kind of good results? Would you be able to get results? The answer is unfortunately no. Okay, so I mean, it's not that obvious. These are all like, you know, research paper after research paper proving these things, right? It just sounds obvious when I say it, you know? But okay, so look, if you take this like ridiculous idea, right? You take a Gaussian to approximate a posterior, that's clearly not a Gaussian. What are you gonna get? Well, if you do this for BNN, this is the kind of uncertainty you're gonna get predictively, which is not the one that we want, right? Because it's real flat here, okay? It doesn't reflect the lack of data. Okay, so what about sampling? Well, it turns out you can do a little bit better with sampling. If you approximate the posterior with samples, usually you can actually get the kind of uncertainty that you want, okay? So not all methods of approximate inference are equal. Some are just clearly better than others, okay, for BNNs. Now the question is, but why is it so hard? Right? Like really for even just fancy kernels, like, you know, kernel regression is just easy. Bayesian kernel regression is easy in closed form. What's wrong with BNNs? Okay, well, it turns out this is why. So this is very recent work that helps us visualize the posterior. So technically it's the likelihood, but in our case, we can pretend it's the posterior. This is what the posterior of a single Bayesian neural network look like. And these are all different visualizations of the same posterior by projecting them randomly into 3 dimensions. So now you can see where the complexity comes in, right? Even in some of the projections, I can see how far away is this posterior from being Gaussian. I can't even begin to quantify for you, right? This posterior is just super hard, okay? So in fact, the picture is even weirder than that. How complicated is the posterior of a BNN? It's so complicated that you can actually find whatever random patterns you want to find by finding a projection. There will be a projection that can create any old pictures for you that you want, right? Which is actually also very interesting recent work. Okay, that's how complicated this posterior is. So there's no way your Gaussian is going to get you anywhere, right? So you're not surprised anymore. Okay, but then actually the question is, right, you can ask it this way, turn it on its head. You're like, but do I need to do a good job though? Right? Because sometimes a crappy job suffices, right? That's just life, okay? So in this case, for BNN, do I really need to do a very good job of capturing the posterior? Or is kind of like a crappy approximation just good enough? Because if we're all looking for just like this kind of blow up and uncertainty when we're away from the data, maybe I could just do a crappy approximation, it'll be fine, right? It turns out, luckily, the answer to that is yes. And we have increasing evidence that this is definitely true. Okay, so for example, if you have a posterior that's that complicated, then usually when you do a approximation by sampling, even that is going to be kind of crappy, right? But even if you do kind of a bad, you know, approximation of your posterior by sampling, you see that you can already get these beautiful uncertainty pictures that have exactly all the characteristics we want. Okay, so the answer is not so sad, or the landscape is not so bleak. You can actually do poor approximations of the posterior if you capture the right pieces, right? The main research question here is we just don't know which are the pieces that's important for us to capture, if indeed what we want is uncertainty, right? That's the link that's missing. Which piece is important to capture, okay? All right, so then the question is, okay, I'm gonna try to end on time. So then the question is, okay, so can we use some sort of metric in order to tell us, right, which models are better at capturing uncertainty, or which approximate inference is better at capturing uncertainty? Unfortunately, the answer to that is also no. Okay, so I know that that's why I went quite fast, but like, you know, so I'm going to explain what that is. So this is joint work with another group of folks at my lab, right, wherein we just basically took all of the fancy inference methods, okay, for inference for BNNs, and we evaluated them, right, using the log likelihood, and then we plotted them out on some toy data sets, okay, to see how good is the uncertainty that we get. Here's the answer. You've already seen this answer before, which is that if you choose to, like if you do model selection based on log likelihood is oftentimes going to select the model for you that captures the data perfectly in terms of its uncertainty, right, where there is data, right, but it will not care what you do with the uncertainty outside of the data. So in this case, log likelihood is going to choose a posterior that does not have the property that we want in terms of uncertainty, right, when actually this is the model that we want, okay? So the story is we can't use our usual metrics in order to help us select a model that gives us the correct notion of uncertainty. And furthermore, when we ran all of these approximate inference methods on benchmarking on these toy data sets, we found that most of them did not give us the right notion of uncertainty, meaning most of them did not give us this picture over here, okay? So that's very sad news, right? Okay, all right, so here's some good news, right? So the good news is it turns out that like you don't need to tackle the very hard inference problem for trying to infer the posterior of BNNs. Sometimes you can just approximate the full BNN model with something a lot easier and you get a lot better results, okay? And so this is what we're gonna do. So what we're gonna do is instead of taking a full neural network model and putting the priors over all of the weights, we're actually only going to take a neural network model and put the priors over the last layer of weights. And we're gonna train the previous layers deterministically using something like, you know, MLE with regularization, right, to solve our task, okay? So i.e. we learn the features deterministically. After we fix the features, we're gonna perform Bayesian linear regression on top of that, right? Which is exactly kernel regression, whereas now the kernel part is replaced by a neural network, okay? All right, so when this models were proposed, everyone got really excited. They were like, all of a sudden, I don't need to deal with BNNs anymore, right? Variational inference, everything inference for them was super hard, okay? So the question is, yes, this model is easier. Does it give us the right notion of uncertainty? And that's the sad part. Not quite, right? So before you get too sad, there's a fix for it, right? But let me just tell you why, okay? And the reason, again, goes with our observation that in order to get good uncertainties away from the data, wide uncertainties, we need functions that extrapolate very diversely away from the data, right? So unfortunately, for these types of neural network models, they're called neural linear models, right? Sometimes if you don't regularize them, then they're able to get very diverse functions in the prior predictive, which means that in the posterior predictive, you're going to get these very diverse functions, right? But if you do ever apply any sort of regularization, which is typical of training, right, then you're going to collapse all of the diversity in the prior predictive, and hence you're going to get no diversity in the posterior predictive, right? But if you're like, okay, well, then maybe I'll just not regularize. Unfortunately, across random restarts, you don't always preserve this notion of diversity, meaning that sometimes you get lucky, you get very diverse prior predictives. If you don't get very lucky, you're going to get no diversity, and you're going to get like this sort of picture. Okay, so the point is that these models, though much more scalable than neural networks, they don't give us the kind of uncertainties we want. So what can we do? Again, the idea is going to be very simple. If you want diversity in your functions, just go and train for it, okay? So our idea for this project, right, with a bunch of really awesome folks, including some really great students, right, is very simple. What we're going to do is make sure that the prior predictive actually can encode functions with a whole lot of diversity. Now, how do you make sure a set of features encode diversity? Well, we introduce what we call auxiliary functions, right? So we're basically, these are functions that are linear combinations of our features that we learn. And when we're training our features, we just make sure that these functions that they learn, right, are as diverse as possible when measured by a cosine similarity diversity penalty again, meaning that we're again encouraging these functions to extrapolate far away from each other by pushing their gradients away from each other, okay? And if you train this way, you're gonna learn a feature set that's capable of expressing very diverse functions, right? Which means diverse posteriors, right? And so what does the data tell us? Well, the data tell us that if you really ran what we have, which is called Luna, our framework, right, on real data, okay, and you train the data, you train our model on a data set that has a gap in it, right? Then you test how uncertain our model is on the data that, is inside the gap, okay? So we're going to train outside the gap, test inside the gap, right? And what you see is for our model, our uncertainty increases for data inside the gap, which is what we want, right? Because that was data that we had not seen before, right? Whereas all the competitors, never mind who they are, right? But their uncertainty, completely uninformative. In fact, they're more certain about the data coming from the gap than they are about the data that we trained on, which is real bad, okay? That is real bad, okay? And so what else do we know? Well, actually, it turns out that not only is our uncertainty more capable of learning where is your gap, right, OOD, we're actually also better at transfer learning, meaning suppose we train outside the gap, right, in the green region, okay, right? And we fix our features, and we retrain the Bayesian linear regression part on the part inside the gap, okay? So now this is a completely different function, right? Our features are able to adapt and do well for the function inside the gap, right? And then other ways of training are unable to do so, right? So the features that other models learn outside the gap cannot generalize to inside the gap. They cannot transfer, okay? So this is saying that not only are we learning diversity because it gives us better predictive uncertainty, but the diverse features that we learn, they're also better at adapting to new tasks. And that should not be a surprise to you, because if you learn diverse features, right, they're good for multiple different types of things, okay? Cool. All right. So then you might be like, I'm going to try to wrap this up in 2 seconds, okay? So then you might be like, great, you guys, you solved the problem, right? You can give us like diversity and uncertainty, wonderful. Yeah, well, it turns out not so much, okay? So, and the reason is because if you think about how do we apply Luna, right, to get really good uncertainty in the classification context, right? It turns out that Luna doesn't help. Okay, so if we think about why, this is because in classification, how do you get uncertainty? It's a bit weird to think about, so I'm not going to go into it, but it's good for you guys to think about maybe afterwards, right? So if you want very high predictive uncertainty for points that are far away from the data, right, it turns out that in classification, what you need to do is you need to make sure that either in your ensembles or in your posterior, you encode circular boundaries. Okay, boundaries that have to properly enclose the data. Otherwise, you're not going to have predictive uncertainty far away from your data. Okay, so then the question is, okay, so, you know, do BNNs and these existing models, neural linear models, are they going to be able to encode circular boundaries and tell me what's OOD out of distribution or not? The answer is no. Okay, these are the types of boundaries that BNNs learn. You see, it does have uncertainty, but it's like straight line uncertainty. It's not sure which line should fit this data set, right? And here's the neural linear model, again, straight line uncertainty, right? Which means that if this is the kind of uncertainty you have, if I'm a point way out here, guess what? I'm gonna be super certain that that point should be classified as red. And I'm gonna be super certain that this point is being classified as purple, right? Because again, these boundaries that you have uncertainty over, they don't encircle the data, okay? So they cannot detect data points that are OOD that are far away from your data. Okay, right, so existing models won't give it to you for free. Can Luna do the trick? No, and here's why, right? Very simple. If you think about pushing two lines away from each other using cosine, when is cosine maximized? 90-degree angle, that's it, right? 90-degree angle, right? Or minimize or whatever, right? So if you maximize a 90-degree angle, well, these two decision boundaries will do it for you, right? Do either of them encircle the data? Heck no, they don't, right? So using our gradient penalty is not going to incentivize these decision boundaries to make full circles, which means that if I have a data point all the way out here, OOD, right? Again, my model is going to be super short that it should be classified as red. Okay, so that is the sad part. So this is a second paper with a bunch of really awesome students and folks I like from my lab. Right? This is how to fix the problem for classification. If you want to encode circular boundaries, again, super intuitive. If you want your features to encode circular boundaries, just make them, okay? Just make them. So what we do is we literally create a boundary around our data. That's what we do. We just literally create a boundary of our data, and we basically force our classifier to distinguish between points on the boundary and points inside the data. That's it, you see? So, which means that if you train a classifier, right, to be able to distinguish points on the boundary and points in your training data set, it has to, by definition, create a circular boundary because you've literally created a circle around your data, right? Okay, which means that if you train like this, your features are going to be rich enough to be able to express circular boundaries. And then, right, when you apply the last layer, the Bayesian layer to it, right, it's going to be able to have it's going to have diversity over circular boundaries in the prior predictive. And hence, the posterior predictive is going to include circular boundaries, right? So what is this plot telling you? This plot is telling you that it's working, okay? That's what it's telling you, right? So I don't have to say it, you can see it, okay? So essentially, this is what we're testing. So we have in distribution, which is the data that we trained it on, right? And then we've held out a couple of classes. Let's say this is MNIST. Maybe I held out the digits 9 and 7, right? And finally, I have just some nonsensical pictures, right? I trained it on MNIST, maybe I trained it on cats and dogs, and then I show it license plates, right? So in general, you would expect the uncertainty of your model to increase, right? As your images get more and more farther away from your training data, right? Which is exactly what we see. Whereas other models do not consistently give us this behavior. Other models can be more certain for OOD points, the data that it didn't train on, than the data that it did train on, right? So this is just showing that the uncertainty that I promised that I was going to deliver for you, indeed, we observe it when we use it in real life on OOD detection. Okay. Furthermore, here's something that's very intuitive, right? So here's an example of me making, so how do we align this with human intuitions of out of distribution, right? So if I take a digit that you recognize, I started adding random Gaussian noise to this digit until you get to the point where you can no longer be sure if this is a digit at all. What should your uncertainty do? Well, it should start very low, your epistemic uncertainty, right? Then it should blow up because at this point, you should not be certain that this is anything looking like your data. And our model is the only model that gives you exactly this human intuitive behavior, okay? Whereas other models may give you something completely uninterpretable, right? Cool. And so that is what I have to say in terms of our work, which is hopefully very exciting. And so what is that work? Let me summarize real quick. What that work is that we're able to now build for you uncertainty-aware, deep Bayesian models that are fast. And fast is really the key here, is that like, we don't do any of that fancy BNN inference stuff that's complicated and horrible, right? In fact, our models, they train as fast as a single neural network, a single pass through a single neural network plus a Bayesian linear regression part. That's how fast it is, right? It's not even an ensemble, it's faster than an ensemble, right? Cool, all right. So on the other hand, right, I do have to point out some drawbacks, which is that maybe I bullied you a little bit at the beginning into that verbal contract where I was like, see, this is the right kind of uncertainty, right? You just have to agree because I'm the speaker here. Maybe some of y'all disagree. Maybe you guys were like, why would I be uncertain in this region here where there's no data? This function clearly looks like a sine function, right? I'm not uncertain at all. Like, what are you talking about, right? So actually, this is asking a very good question, right? Which is current research, is actually how do we define what is good uncertainty, right? In a task-aligned specific way, right? How do we in general encode domain or expert knowledge into our priors so that our uncertainty really aligns with what we want for that task? And furthermore, are interpretable, right? So that is what we care about. Not just it's wider here, it's not wide over there, but we want it to be really flexible for each task, okay? And finally, we're interested in also learning under heteroscedastic noise. So far, all the models, I assume that the aleatoric noise had constant variance everywhere, but we don't often see this in real data. So we want to learn under heteroscedastic noise. And then finally, we want to make a theoretical connection between kind of like the types of model that we do, right? Where we fix the first layers, only put weights on the priors on the last layers. Well, that's like a BNN approximation. So how do these two models theoretically relate to each other, right? So that's kind of interesting. And other areas of interest that I have in general are outside of this kind of uncertainty quantification is kind of theoretical asymptotic properties of BNN that's related to double descent, properties and applications of deep generative models like VAEs and things like that, and then also human optimized explanation systems, right? So that's in the context of interpretable machine learning. Okay, and so that's it. That is all I have to say. So thank you, and I will take questions. Cool, and I was not too late. Okay.
Hello?
Yes, go ahead.
So I had a question. This is very interesting. Now, a couple of years ago, there was a paper out of MIT grad student, where they were looking at Google's, Google has this image recognition network so that, it'll say it's a mountain, it's a dog, and so on. And what they did is they took and put some very small amount of random noise on each pixel and put it in. And a human would have absolutely no trouble telling these apart, but this thing completely fell apart. It couldn't classify anything. So I was curious, your Luna approach with the BN Luna and all that, the last model that you presented, would that actually be able to solve a problem like that?
Yeah, so that's really interesting. So that's also a different area of my research interest. I forgot to write it down, but it's kind of like adversarial robustness, right? So the kind of adding white noise to something that wouldn't fool a human, but would fool your classifier is called adversarial perturbation. Oh, that's just one example of adversarial perturbation, right? And there, it's kind of interesting. It has more to do with, so generally, like for that kind of particular attack, right? One way to make it not happen that way, right? Not the classification be so sensitive, is if you just sort of regularize your decision boundary, right? If your decision boundary is not like super wiggly, right? If your decision boundary is just like really wiggly, like here I'll draw, like really like this, right? Then if you had a point that was like dog, and then like, and you use made a small perturbation, all of a sudden it's now cat, even though it don't look like a cat, right? And then the fact that your small perturbation is able to trick your classifier is because, your classifier is somehow over catering to your data set, right? It's doing this sort of behavior, right? So that problem can generally be solved with some regularization or other types of training called adversarial training, where you inject noise at the beginning anyways. So a deeper sort of question, and maybe this is a paper that y'all would like to read, it's called Are Adversarial Examples Features or Bugs, right? So now that area of research is kind of like getting into this interesting question of, but are adversarial examples always showing you that your classifier is learning something ridiculous? or sometimes adversarial examples actually changing the data in a meaningful way that you just didn't notice, right? And so it's not like, well, I just added some Gaussian noise to it, therefore my classifier should just think that nothing has happened. That's not true, you know? Sometimes when you add Gaussian noise to maybe like a medical image, right? Like you can really make a tumor look like another type of tumor, right? So sometimes when you add these adversarial perturbations, you've changed the nature, you've changed the signal, not just the noise, right? So actually it's a very interesting kind of like area of research that I'm also doing a project related to this, is kind of like figuring out which part of your perturbation is actually changing the signal, right, in the image versus which part is only changing the non-relevant part, which is the noise, right? And it's not that obvious actually.
So one other thing is that, so it's kind of what you're saying is that you do have to kind of have an understanding of your domain and what you're trying to do and build in some type of prior, right?
Yes.
As a realistic point.
Right, absolutely, right.
In
And this
other words,
is,
as opposed to, sorry.
yeah, no, go ahead, yeah.
Well, as opposed to when you use a neural network where you're just feeding it a whole bunch of pixels and saying, okay, I'm just going to find out all this stuff out of it. You still can't get away from the fact that you have to have some level of understanding what you're expecting, or sort of what are the underlying physics, or what, just, you know, you can't use it blindly.
Yeah, I agree, right? So for a lot of folks who, you know, feel queasy about neural networks because we treat them like black boxes, there's a lot of now ongoing research about kind of how to imagine what different parts of your neural networks are doing in terms of, I call them feature extractors, right? And most people in images like NLP also call them the same thing. Like, so we can actually visualize, right? We don't need to have a neuron by neuron understanding, just like I don't understand what each neuron in your brain is doing, but I have a general functional view of what each part of your brain, consisting of different groups of neurons, is doing, right? And it turns out you can get the same sort of understanding for neural networks, in which case you can feel more comfortable about the way that they're reasoning, right? So now we have a lot of techniques that exposes the inner workings and the reasoning process of neural networks that makes them less black box. I think where the innovation hasn't saturated to or penetrated is in the area of prior choice, right? When you're now being Bayesian, maybe I understand what a neural network is doing, especially things that work with images like CNN or natural language processing, right? Like RNNs and LSTMs. But you know what I don't understand is my choice of prior, because that is like just ridiculous, right? Even for polynomials, you know, it's like if you're fitting a polynomial, you're like, yeah, my priors are normal because they're conjugate. I'm like, really? You really believe your prior is normal, right? What does that even mean? Like, what physics are we talking about here with normal priors, right? Like, it doesn't correlate with anything in real life, right? So actually our lab and other labs as well, there's a lot of people working on like incorporating functional knowledge, real science knowledge into the prior. So we're not just like, oh, I understand what a neural network does, and all of a sudden I'm randomly going to choose normal priors for everyone, right? We're going to choose a smarter prior, right? And I particularly think that our framework, Luna and Bacon, allows you to do that, because the feature extraction part, like I said, you can use already existing methods of understanding neural networks to understand what features you're getting, right? And because the model is so simple, it's just like, get me some features and do a linear regression on top of that. There's a chance that I can make this prior mean something, because I only have like 5, you know, if you have 5 features, I have like 5 priors. I can try to make this mean something, right? And that's exactly what we're working on now.
Thank you. Thank you.
How do you integrate the OOD algorithms? Do you run it as a single pass, like data pre-processing to relabel things, or how is it integrated?
Yeah, so for OOD, for classification, for Bacon, so what we do is actually, once we don't actually, so a lot of OOD detectors, right, like what they do is you have to train with a set of data that you knew beforehand was OOD. Well, I'm like, well, if you already know what's OOD, then what's the point, right? Like just make it a third class, you know? Or you know, but if I know that this set of data is OOD, I can't necessarily extrapolate to say, well, here's another set of data that's also OOD, right? So the advantage of our method is we don't actually need pre-label OOD points. What we do is we generate them ourselves, right? We literally take this data. I don't need you to tell me what's OOD. I'm just going to draw a boundary over it. Like there you go. I made my OOD points, right? And then when I train my model, it's going to learn circular boundaries, which means that in the posterior, all my boundaries, they look like this. You know what I mean? Which means that if you have a point that's way over here, it's going to have super high uncertainty, right? Because, you know, it's going to be like, oh, maybe it's red, maybe it's blue, but, you know, I could have any number of predictions. I'm not going to be like, oh, yes, it's always red, right? So that's the idea. So you can actually, you don't need an OOD detector. Our model is an OOD detector, right? As in like, if our model gives you very high epistemic uncertainty for a point, then you have reason to believe that it's OOD. And if it gives you low epistemic uncertainty for a point, then you have to reason to believe that it's in distribution, right? And that's what this plot is basically telling you. See, if we actually took images that we didn't train on, look, uncertainty is super high, right? And images we trained on, uncertainty is low. And images that we trained on by slightly different classes, right? We train on 1 and 2, you show it 7 and 9, right? Uncertainty is slightly higher, but not super high, right? So it's kind of intuitive like that. So you use the uncertainties from our model to do OOD detection, basically.
I have a question.
Yeah.
This is a fantastic talk. Really, really great. Thank you so much.
Thank you.
So this is a really, really simple-minded question, and I apologize if
no, the simple questions are always the deepest. This is what I find, right? Like,
here we
honestly.
go. It seems to me like the disadvantage to some of the examples that you had is that they're really like artificially constructed examples. And what I want you to do is I want you to build up for me a model that I take, you know, some sort of generalized deep learning model, throw it at my problem, and then it comes back and it says, I've got the answer, but this is my degree of uncertainty about my answer. And that's what I want you to do. It sounds like you'll be able to do that if I come in already knowing the distribution of my different classes and how intermingled they are and exactly what the shape of that is.
Well,
if I
hopefully,
know that, that's exactly when I want to use deep learning. If I knew it, I probably wouldn't be using deep learning to begin with.
Exactly. Yeah. So generally we think of it like somehow we're in the middle of both extremes, right? Which is that, like, you know, oftentimes what's hard about modeling is you work with collaborator with domain knowledge and they're like, well, just build me the thing, right? That does the thing, right? Because that's what you do, right? And then, so they either just tell you, here's the result that I want, or else you're solving a problem that's super toy, right? Like you said, I already know everything about the problem. I know exactly what the ideal behavior is, right? So we like to think of ourselves as somewhere in between, right? So as in, like, think about it maybe like this, right? So here, for example, you know, if you're specifying, if you're, for example, specifying, like here, we're generating the OOD points, right? Just say, here's some example of OOD points. Now, imagine rather than doing that, right? Imagine if you can somehow incorporate domain expertise, but from someone, but not like so much as they can specify the distribution of anything for you. But imagine a clinician can like look at a patient and say, you know what, this patient looks very unusual. Here's an example of a patient that would be OOD, right? And if you show them another patient, they'll be like, well, actually, you know, they look fine to me. Imagine if you could get a partial labeling of points like that to use as your exemplar, right? And imagine maybe your, you know, model is able to create some sort of a function that extrapolates between your few points of exemplars, right? And this is actually something that we're trying to do so that it's not like, I don't think you can ever hope for a model, right, that goes in out of the box and gives you exactly what you want, because that's the point I'm making here, is that if you don't already know kind of the behavior that you want, it is very easy, right, to apply your metrics very blindly and literally choose the model that does the opposite of what you want, right? So that's the dangerous part. Now, how much do you need to know? This is the part that I think our lab, you know, we like to work with domain experts a lot. We think that it should be kind of a process between modelers and, you know, domain experts to build models that are very specific for a task so that we can mine the knowledge that they have in the context of their domain knowledge, right? And try to incorporate it so that you don't get a blocks off the shelf model, but you get one that's like going to be designed specifically for your application, right?
So,
does that sort of make sense?
Yeah, so I'm sorry, I didn't phrase my question quite precisely. So maybe it seemed to me like what you really ideally have is something that just tells me how different the particular input that I gave you is compared to your training data. And so don't you just need that and then you're done?
Yeah.
And that's kind of like putting a circle around your...
Fantastic question. Yeah, so actually, so yeah, there are, by the way, OD is not like we invented. It's like a super old field with lots of really cool, interesting stuff related to one class classification, by the way. So where it's like you do binary classification, but you only see examples from one class. Weird, right? But you can do it. So there's tons of techniques that are like this that just says, how different is this point from your original data, right? You can also do it with like density estimators, like generative models like GANs and VAEs and normalizing flows. But there the issue is, again, I think that I would not advocate for using any model without domain supervision, because you might think it's naive, right? You'd be like, okay, this is what I want, right? Or this is what the model will do, right? Uncertainty grows linearly with respect to distance from training set. But why linearly, you know? And how big should that coefficient be? You see what I mean? Right? So it's just like, without you telling me what the physics is, what the biology is, it's really hard for me to just give you a mathematical model because there's just too many, right? That's the problem. And also another thing I pointed out was that oftentimes it's not true that you want uncertainty to always grow, right? Because look, you know, look at this function. It's a sine function. It's very clear to me that it's a sine function. I don't actually care if you have uncertainty here because that's a super tiny gap, okay? And I think that your function is not gonna go crazy here, you know what I mean? So sometimes like your domain expert might even say, look, I know that you think this point is OD because it technically, yeah, it's very far from your data, but really as a domain expert, as a doctor, it just doesn't look that unusual to me, right? That's just a patient that you could see, you know what I mean? So I think that there needs to be flexibility in your model, even if it's just a binary answer model like OOD or not OOD, that model has to take kind of domain constraints into account, right? Otherwise you just can't count on it giving you anything reasonable, right? Is that a better answer to that question?
Yeah, I think what you're saying basically is that there's lots of different choices that we can do, and there's lots of different ways to play this game. And if you don't have a domain expert, then you're gonna just pick something at random.
Yeah, you literally can get whatever answer you want, right? This is kind of the scary thing, right? So your domain expert is key there, yeah.
Even in cases where you have domain experts, you can have, for example, judges. I remember a study where they looked at sentencing by judges, and the diversity among those sentences for very similar crimes and similar situations was extraordinarily diverse. So the question becomes, supposing if one were to use a model such as yours to be able to, say, systematize sentencing, it would have to take into account this huge diversity. So it seems to me like you have to then apply artificial boundaries in order to make it work in that kind of scenario.
Right. So it's kind of like, right, exactly, you know, to your point of how much like uncertainty should I have, you know, because you could have like uncertainty 2, it could be equal to 3, and maybe even relatively it works out. You could be like 2 is bigger than 5, you know what I mean? But guess what's also bigger than 5? 100, you know? So what exactly is this bound and when is it meaningful, right? I think it's something that, you know, we're struggling with, and also we're trying to solve in a task specific way, because I feel like you can't really answer this with statistics or math, right? You just have to do it with respect to the task, right?
It could even be bimodal because you
exactly
judges and
absolutely
judges, if you will.
It's actually very interesting, you know, so when you work with like one of the models we have worked with in the past on a previous research project can produce exactly for you bimodal uncertainty, right? Which is actually very exciting because many kind of maybe in real life, your uncertainty is indeed bimodal, right? It's not like centrally clustered at some value, right?
Right.
Okay, can I interrupt?
Yes.
Thank you, everybody. Way excellent talk as usual. I think we're gonna maybe stop now. You can contact Weiwei. Your email should be on the bio, right, on the website. That was a great talk. Thank you again. Let's thanks Weiwei again. And thanks everybody for coming. Next seminar is next week.
Cool. All right. Well, thank you, everybody. That was a pleasure. And thanks for having me, folks. Hopefully some of you, I will see you in class. Okay. Some other of you, maybe I'll run into you at some other seminars and events around here. Cool. All right. Bye, everybody.
Bye. Thank you.
Thank you.
Thank you.